Hello everybody, welcome back to another video. This video is going to be on Calc 2, where I'm going to be discussing the area between curves as the start of a new series. And I'll help you through all your Calc 2 issues. Let's begin, area between curves. So to first understand the area between curves, we want to first understand how to find the area underneath one curve. Alright, so to do this, this is the graph, x squared. So to find the area underneath this curve, we have to set boundary points because we can't just find the area from like whoosh. But let's find the area between A and B. And what we do is using the integral, we can approximate small rectangles at each, just like a lot of freaking rectangles everywhere. And we'd add them all up. Now at every given moment, these rectangles have the width of dx, so an infinitely small change in the x direction, and the height of whatever that function is. In this case, it's f of x, which is equal to x squared. So when, let's say this point was, for instance, like 3. Let's say this was x is equal to 3. This is just like an example. So x is equal to 3 at that point. So at this point, we know this rectangle has, so x is equal to 3, therefore f of x so this rectangle at when x is 3, the height is 9. And we do that with integration through for every single infinitely small case along this graph. And it looks like, so we integrate from a to b, left to right, of the function, the height of the rectangle multiplied by the width of the rectangle, and we integrate that. Now let's have a real case. Let's say this was, I don't know, let's say this was 2 instead of a, and this was 4. So we would integrate from 2 to 4 of f of x. So f of x is just x squared. Because again, f of x is just the height of the rectangle multiplied by the width of the rectangle. And this is equal to x cubed over 3, evaluated from 2 to 4. And this is nothing but 4 cubed over 3 minus 3 cubed over 3. I really do not feel like calculating that out right now, but that would be your answer, unsimplified. So that was area underneath one curve, but we're looking for area underneath two curves. Let's draw the graph again. Let's use the example x squared again. But because we're finding the area between two curves, we add another curve. Let's call h of x. So h of x is a straight line. X squared looks like this. Now, the places that they intersect are very important because we want to find this area. We want to find the area between the two. Now they intersect where the heights are the same, for instance. So where f of x is equal to h of x. So we'll get x is equal to x squared. And from this we can bring this x to the other side, we get 0 is equal to x squared minus x. And again, 0 is equal to x bring the x out. So then we know x is equal to 0 or 1. So this is 0. That's the origin. We knew that. And this is when x is equal to 1. All right. So also, just a key note, I knew that from 0 to 1, I knew that the h of x, or x, was higher than x squared, because from 0 to 1, when you square a number smaller than 1, it actually gets smaller. And after you surpass 1 and you square it, it gets exponentially bigger. That's why it gives a little divot in a way. So now what the game plan is to do the exact same thing that we had here. Set up rectangles. So we want to set up rectangles. We want to set up a rectangle here, 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 here. We want to set up all these rectangles. Now notice how these rectangles don't actually have, it doesn't touch the bottom of the graph like it did here. Instead, they stop at the bottom of this bottom graph, f of x. So let's look at what one of the rectangles looks like. So one of the rectangles has the width dx, as the width of it's still infinitely small in the x direction, but the height is a lot trickier. So its height is the portion, I'm just gonna mark it up. The height is that black portion right there. And what would that height be? Well, this part right here, the top part right here, is nothing but x, or h of x I should say. And the bottom and this bottom height is nothing but f of x. So this is h of x up until that point. This is f of x. So the difference would give you this middle area. So the height of the rectangle would be h of x minus f of x. Because in doing so you have h of x at the top minus this tiny portion down here, it gives you the middle guy. So everywhere we look, we have this property. At this moment right here, this rectangle, the absolute height of this guy would still be h of x minus f of x, because we have to take the bigger height minus the smaller height. That's what we're doing. And now we have to integrate that from 0 to 1, because that's where the area is. It's a very messy picture now, but so from 0 to 1 of the height of the rectangle, so the height of the rectangle is h of x minus f of x multiplied by the width of the rectangle. All right. So the height of the rectangle, we can rewrite this as h of x is x minus x squared. And I think you should be able to solve this integral. This would be x squared over 2 minus x cubed over 3. All solved from 0 to 1. So you get a half minus a third minus 0 goes into there, 0 over 2 minus 0 over 3. This is 0. I don't want to do this either, but I mean I can, but I don't want to. So that's how you find the area between two curves. Now, another way to look at this, we'll put this aside for a moment. Another way to look at this is, instead of do the height of the rectangles that you're using, you can look at it as subtracting the total areas. And what I mean by that is, let's get back our f of x, which was x squared. All right. Let's get these guys back. So this was f of x, this was h of x. Now instead, we could look at it. So the area between these two guys is this orange piece that I'm going to color in. Okay? But think about it this way. The area underneath h of x is everything here, including the orange bit. Okay? So that's the area of h of x. I'll redraw that. Well, this is from 0 to 1 as well. So this is that pink thing that I wanted to draw of h of x. And then you also have the area underneath the curve of f of x. It's harder to see because I kind of screwed up the drawing, but I'll show you. It's this guy right here that I'm trying to show you. So look at these graphs. So this is f of x. So look at these graphs. I guess I didn't draw into proportion, but basically, when we take the h of x area, subtract the f of x area, so if we take this entire area, subtract by this smaller area, we'd be left with this orange portion. Does that make sense? I wish I had a cool animation to show you, but here to prove you why that works as well. So basically we're taking the area of h of x from 0 to 1, of course, subtract the area from 0 to 1 of f of x. And then we should get the area between the two graphs in this little area there. So I'll do that. Of h of x dx, because we're making the small triangles. Sorry, small rectangles who have height h of x and width d of x, subtracting 0 to 1 of f of x. So this is rectangles that have height f of x and width d of x. And using a property, we can bring out this integral from everything and get h of x minus f of x dx. And that's nothing but x minus x squared dx. And that's exactly what we had on this one. So in this one, we were looking at the height of the rectangle and trying to find the height in between it, what the height was. But for this one, we're calculating the areas and subtracting them. And we ended up getting to the same exact spot as we were in both cases. So either way that you do it is perfect. It makes no difference. It's just a different way to understand what you're doing.